Yeah, we can start. Just a second. Chintan, okay. We are live streaming on YouTube. Have you
Yes,
started? Okay.
yes,
Okay.
yes. And yeah, good evening. It's 16:30, and we are here for the sixth day of the Science Week. Well, it started last Saturday, but then a couple of days in between there was no program, and we are on the sixth day of the program. And we are very glad and happy and honored to have Professor Rohini Godbole among us today. She belongs to the Indian Institute of Science, to the department which is now called Center for High Energy Physics and used to be called Center for Theoretical Studies, right opposite my department, which is mathematics. Used to be right opposite, has moved there from now. But if you go to Rohini's webpage, you will see a very nice photo of her in that building where it was housed before. I strongly recommend that all of us visit Rohini's webpage for various information. Professor Godbole is very accomplished in her field. She is a Padma Shri. And well, I'll mention only a few of the awards because it's a long list, and I'll finish all of 1 hour if I wanted to mention all of them. She's a fellow of all the three academies of India. She's a fellow of the World Academy of Sciences. She's a J.C. Bose Fellowship awardee. And well, these are her academic accomplishments based on her research, but we are today here listening to her for a different purpose, and she's very accomplished in that as well. She loves speaking to young school children and college students about and gives popular talks on physics, and that's what we are looking forward to today. So Professor Rohini Godbole is going to talk to us on particle physics today. Professor Godbole, it's yours.
Thank you very much, Professor Tirthankar. And it feels strange to meet people online when one is used to having seen them across the road. But the last 2 years have changed everything. And I think this is the first time I set my eyes in the last 2 years on Professor Tirthankar. So I am truly very, very
Yeah.
happy and pleased to be participating in this science week. And I am sort of, as was told by Professor Tirthankar, this is something I quite enjoy to talking to people and try to tell them or try to convey to them what is the beauty of the subject that drives me and that attracts me, and I want to somehow share that so that you can and see whether you people also share my enthusiasm for this subject. So today I'm going to be talking about subject which is particle physics, which is the area of my research for the last 40 odd years. And I have given a kind of a very all encompassing title. I want to talk, and I want to give you a sort of a very bird's eye view of the subject of particle physics, and I want to try to take you from the heart of the matter to the edge of the universe. And doubt very much that I'm going to be able to go into details even at a popular level, but I would direct you to these two articles which I wrote and which are kind of appropriately directed at, I would say, at the BSc students at the BSc level, and the second one in the physics news is perhaps even at the 11th and the 12th level. So you can have a look at these two articles. So what am I going to talking about? As I said, from the heart of the matter to the edge of the universe. So looking, how have we looked at historically at the heart of the matter? So all of you, I'm sure, know about the famous Rutherford experiment where Rutherford discovered the nucleus. So the Rutherford scattering experiment, which we will discuss in some detail, actually probed the atom to begin with. Then something else which you will not have read or heard in your books is how a very similar version of Rutherford's experiment at the level of a proton discovered that even proton is not point-like, but that it has a structure. So I'll try to tell you about these experiments. In fact, the scattering experiments have gone on much further, and there are these electron scattering experiments with electron microscopes, which actually can take even a picture of a DNA in some indirect way. And these are the sort of things as to how you look at the heart of the matter. But apart from visually looking at what lies at the heart of the matter, particle physicists also try to understand, in fact, also how things work at the heart of the matter. And how things work at the heart of the matter, so what is at the heart of the matter and how do things work together, is actually the subject matter of the subject of particle physics. So how do things work at the heart of the matter? There, through a series of very expensive and big gadgets, particle physicists, in fact, work with these big collider experiments where beams of high energy particles are accelerated. These are actually magnets in the tunnel of the Large Hadron Collider, and the beam of particle is going through the center here. So in particle collisions, when protons moving at almost the speed of light scatter off each other, one studies more about what lies at the heart of the matter and how do things work at the heart of the matter. And India participates in this. In addition to that, particle physicists also need kind of experiments where the neutrinos, one of the ghost particles that come to us from the universe, from outside, from cosmos, atmosphere, everything, how to catch them and how to do experiments with them. There are many observatories and experiments planned around the world, and I'm glad to say that there is one which is called Indian Neutrino Observatory, which has been planned for quite a few years, and we hope that it will take off soon. So these are the experiments, these are the apparatus that look at the heart of the matter. But I also told you that I'm going to say that how particle physics is somehow also applicable to physics that happens at the edge of the universe. So how does that happen? And here now, again, India, I'm only indicating things in which India is participating. And there are these two famous experiments, Laser Interferometry Gravitational Wave Observatory, LIGO. And what I'm showing you here is the artist's conception of LIGO India, for which the sanction has been already granted, and the scientists have the money to build the laboratory. And this would be looking for gravitational waves coming sometimes from the edges of the universe. Then there is another experiment called Square Kilometer Array of radio antennas. So they will be spread over a huge area, and the square kilometer refers to the collecting area of these antennas, and they will be somewhere based in Australia and South Africa, so that there is very little radio noise, because you want to look for radio waves which are coming from within the far reaches of the universe. And believe it or not, the particle physicists have something to say in these experiments as well as these experiments, and it is this that I am wanting to get to you and convey to you. So this is my idea. So first what I will do is that I will talk about how the structure of matter has been revealed to us as layers within layers within layers. So I will follow this inward journey in some detail as to how did this journey really happen, and how in principle we have arrived at the current knowledge of what lies at the heart of the matter. Then maybe a slide or two to tell you what did we learn and where next. And that where next is actually the story of the outward journey going outward to the edges of the universe, which is in some sense the future of particle physics. So, historically, I don't know, now you people, most of you people are very young. But when I was, very young, we used to have, cans of oil on which there will be a little girl sitting and the mother would be cooking, And in that picture, there will be another can of oil. In that can of oil, there is another picture of a mother cooking and a little girl sitting, and so on and so forth. So that would be like picture within a picture, within a picture, within a picture, within a picture, within a picture. And the idea would be, is this what the structure of matter is all about? Or is the structure of matter essentially like a Russian doll, where you take one doll open one doll, you find another doll inside. You open it, you find another one. But beyond, when you reach the last doll, then actually when you open the last doll, which is this here, all you find is nothing, just air, free air. And the question is how we really reached, how we taken out, separate the Russian doll of matter completely. And we do believe that we have reached the innermost layer when it comes to the structure of matter. So what do we know? When I said layers within layers within layers. So there is a lot of information on this slide, but I would like you to concentrate right now only on this one vertical column here, okay? So many, we learn this in the school. We say that matter comes in 3 states: solid, liquid, gases, okay? So whether it's nitrogen, which is liquid nitrogen, or nitrogen gas, or maybe, if it's carbon, whether it's a solid carbon, whether it's a liquid carbon, and whether it's a gaseous carbon, right? So these are 3 stages of the same object. But then one finds that what makes carbon a carbon, what gives oxygen the properties of the oxygen, are actually intact when you keep on making them, smaller and smaller pieces of it. And the smallest piece of oxygen that has all the properties of oxygen is actually an oxygen molecule, or here in this case, I have written a water molecule, because I can think of water, vapor, and ice. So this is a H2O molecule. But this H2O molecule is also not, by itself. It is made up of atoms, 2 hydrogen atoms and 1 oxygen atom. And how does that get held together? Oh, it gets held together because each of these atoms consists of a nucleus and electrons that are orbiting around it. And it is the electrons from each one of these, hydrogen and oxygen, that actually bind these hydrogen, oxygen, and hydrogen together to make into a molecule. So the gases, for example, or material is made up of molecules. Molecules are made up of atoms. Atoms are also not fundamental, but they are made up of a nucleus and an electron. So is the nucleus then fundamental? Oh no, a nucleus is further made up of what we call, nucleons, which are neutrons and protons. So, okay, can we say the world is made up of neutron, protons, electrons, and that's it? No. As a matter of fact, the neutrons and protons are also made up of something which we call quarks. And right now, with all the energy, and what I have not discussed in detail, but what is shown here simultaneously are 2 things. One is the sizes, which I will discuss in this picture in a minute, and the other is the energy that I have associated. So how much energy do you need to dissociate a molecule? Oh, that's not too much. You can connect a battery, and few electron volts, you will separate the molecule into positive and negative ions. Then you want to separate a molecule into atoms. You need to do a little more work. Your battery needs to, you need to increase the voltage to something like 100 volts. Then only you can separate atoms from each other. But now when you want to look at the fact whether atoms are made up of electrons and nuclei, as we will see in Rutherford's experiment, we needed alpha particles which had the energy of about 1 million electron volts. And to learn that a nucleus is made up of neutrons and protons, actually we needed electron beams which were made up of energy which was 1,000 million electron volts, and 1 million electron volt is 1 million electron volt. So 1,000 million is about 10 to the 9 electron volts. And if you increase the energy even further by 20 times more, we realized that the nucleus and the neutrons and the protons are actually made up of quarks. But now we have actually increased these energies, and this is the journey which I will tell you about. And what we have found is that quarks, there is nothing below the level of quarks and gluons. So let us get an idea about the sizes. So if I say that the atom is 1 unit, then the nucleus is about 10,000 times smaller than an atom. And a proton is about 100,000 times smaller than an atom. And a quark and an electron, we have really found no proof that they have any size. But the scientist very strictly experiments, and only experiments if I am going to rely on, will tell me that a quark or an electron has a size which is, if at all it had a size, it should be smaller than 100,000 times than the atom. Now this is in terms of atom. But how big is an atom? Many of you have learned as in the 12th, and as well as if you are in BSc, you have learned it even further. Size of an atom is about 10 to the minus 10 meters. Okay. And size of, therefore, if you apply these factors of 10,000, 100,000 and 100,000, you will realize that the size of a nucleus is 10 to the minus 14 meters and size of a proton is 10 to the minus 15 meters, and electron and quarks at the largest will be 10 to the minus 18 meters. So once again, to repeat the sizes, the constituents of matter at different distance scales are different. At a distance scale about 10 to the minus 10 meters, we think that the constituents, the constituents are atoms. But it ends finally with quarks and leptons, which are 100 million times smaller than an atom. This is what I have said here, 100 million times smaller than an atom. And we believe them to be point-like. If at all they had a size, the size is less than 10 to the minus 18 meters. And how have we learned this? We have learned it using experiments at high energy accelerators and the simultaneous development of theoretical models. This together have helped particle physicists, nuclear physicists, atomic physicists to finally arrive at this understanding. So before I go on and tell you the story about that, let me try to give you a feel how small is 10 to the minus 18 meter is. So let me begin by a photograph. This is a set of photographs that I have taken from a website of the laboratory CERN. And this is actually a photograph of a patch of rose flowers. And I used to be able to see these out of my window in my office at CERN. So this area represents a square 10 meter by 10 meter. Now let me try to zoom in. What does this mean? Let me try to increase the resolution by a factor 10 so that the same square now represents an area 1 meter by 1 meter. So now obviously you see your small fraction of it, so you see a bigger resolution. Now I increase the resolution or zoom in by another factor of 10. So this is 100 actually. This is 1 meter by 1 meter. Now I go to 0.1 meter by 0.1 meter. So each size I reduce by 10 factor 10. So the total area is reduced by a factor 100. Now I begin to see the leaf, on a particular leaf, I begin to see a fly. Now 0.1 by 0.1 meter, same area. Now I say same length. Now corresponds to by zooming it by another factor of 10 to 0.01 meter by 0.1 meter. That's 1 centimeter by 1 centimeter. And here now you begin to see much more details of the fly. Further, when you go by another factor of 10, so you realize now we have come to only 10 to the minus 3 meters. We have to go down at least 10 orders of magnitude before we see anything more. So here what do we see? We start seeing the, this eye, the complex eye of the bee. And here we begin to see something, Now if you go by another factor of 10, you actually begin to see the base of the sensor, okay? Another factor 10, okay, here from 0.001, another factor 10, 10 to the minus 5 meters by 10 to the minus 5 meters, you begin to see this sensor with which a bee sees things. Then this becomes the base, another factor of 10. Now this base is made up of DNAs, and this is what you begin to see the strands when you increase the resolution even further. And indeed, if you take photographs with the electron microscopes, you would, this is now an artist's reconstruction. What you measure is something different, but you reconstruct, and what you are really seeing is that these strands are actually made up of this double helical DNA. So remember, my first thing here was 10 meters by 10 meters, and now the same length corresponds to 10 to the minus 8 meters. So I have gone down 10 orders of magnitude. And now if I go down another 2 orders of magnitude, that is this box, I zoom in by another factor of 100, then actually I begin to see that there is a nucleus here and there are these electrons orbiting around it. This is a carbon nucleus, which is of course there in a DNA. And finally, from this 10 to the minus 10 meters, I go down another 4 order of magnitudes, and then I begin to see a proton, which is made up of quarks inside, rather a nucleus, which is made up of the nucleons, and another factor of 10, and I begin to see a single proton made up of 3 quarks and 10 to the minus 15 meters. And so far, we have not been able to find evidence of any structure of the quarks. So this is where the zooming in stops. But this is really what a 10 to the minus 15 meters means, and 10 to the minus 18 meter means that you're going to zoom in 3 times more. Actually, this 10 to the minus 18 meters is a very interesting number, because the LIGO experiment, about which many of you would have read in the newspaper, which discovered gravitational waves, actually measured a displacement using again interferometry, which was 10 to the minus 18 meters. So this 10 to the minus 18 meters is somehow really the limit of our measurement accuracy right now, and different tools. Now, the development in human understanding has revealed such layers within layers within layers, and the methods that uncovered this structure, and funnily enough, has remained exactly the same. And there are mainly 2 different ways in which we, the scientists, have inferred what lies at the heart of the matter. There are static methods, that is, we use the systematics that is observed in the properties of the system at the macroscopic scale. What is meant by that? Pressure, volume, mass, spin. So, for example, you find that the oxygen molecule weighs 16 times as much as the hydrogen atom, and then you say, okay, most probably the oxygen is made up of hydrogen, but since the charge on a hydrogen nucleus is only +1, and charge on an oxygen nucleus is only 8, then the oxygen nucleus must contain something very much like a proton, which has the same mass as the proton, but which doesn't have a charge, and that's how you can infer there lies neutrons, and therefore that the oxygen nucleus is made up of 8 protons and 8 neutrons. Now, these kinds of arguments, a very fancy word for this, which you will read in literature, is symmetry. And the second is scattering experiments, whether you use scattering of a probe from a body and you get information about the structure of the body. And what is amazing, and I think that is what has kept thousands of particle physicists glued to the subject for the last 100 years, is that the basic laws of physics that we discover at the distance scales of the nucleus, nucleons, and the quarks and the leptons, the same basic laws of physics can actually explain behavior of matter of all shapes and sizes. Now you can ask, that's very fine. You can understand why water shows 3 phases from first principles, but do these laws of elementary particles governing this behavior of objects at the heart of the nuclei of atoms have anything to say about cosmic observations? And the answer is yes, not just in principle, but in practice. And that is really the connection to the edge of the universe. So, for example, let me talk about cosmic distances, which are millions of parsecs. And 1 parsec is roughly 200 times the Earth-Sun distance. And the universe is megaparsecs. Mega is millions, right? So size of a nucleus is 1/10 of a billion centimeter. I showed you. Electron size is less, if at all it had a size, less than the billionth of a meter stick. And the amazing thing is that the laws of physics that we discovered at these distance scales are necessary to explain what happens at cosmic distances and what happened billions of years ago. That is, it is necessary, apart from astrophysics and other classical physics, we also need to know particle physics to be able to explain why do we exist. What is meant by that, much more or less dramatically, is that why does our universe contain much more matter than antimatter? I will come to all this, so don't worry. Why does most of the matter in the universe not shine? That is the so-called dark matter. Why is this universe not just expanding but accelerating? That's the dark energy. And interplay of this physics at the micro scale of billion centimeter, 1/10 of a billion centimeter, billionth of a centimeter, and the physics that happens at parsecs, megaparsecs, and the physics that happened at the beginning of the universe in billions of years ago. This interplay of physics at the micro and the macro scale is actually what helps us to further increase our understanding of laws of nature. How we look at structures, For example, if we want to study galaxies, what do? We actually go and look at a, radio telescope. One of the things that we do is look at a radio telescope. That is the GMRT. I will talk a bit about that. Then, if I just want to look at Jupiter and Saturn's rings, an ordinary telescope will do. If I want to see a dog, which is a few meters, I just need to use my own eyes. If I want to look at a cell, which is much smaller, then I start looking at an ordinary microscope. When I have to look at a DNA, I already showed you, I need an electron microscope. And when I want to look at the inside of an atom or inside of a nucleus, I actually need very highly accelerated particle beams. So this is a meter stick, and these are actually distances that I showed you pictures of, that the nucleus is 10 to the minus 15 meters, and whereas an atom is about 10 to the minus 12 meters, 10 meters. So we have seen these distances, and this is this journey from here. I would actually take the journey from here and go in the story and try to tell you this story. So, Greeks, if we ask what were elementary things from the times before Christ, that is from BC, the Greeks had said that there are 4 elements, earth, water, fire, wind. They are called elements in English for good reason, because the Greeks thought that everything was made up of these 4 elements. And then came Democritus, who said that by convention there is color, by convention there is sweetness, by convention bitterness, but in reality there are only atoms and space. So Democritus was actually postulating that all the properties that we see around us for the matter are really because of some, funny things called atoms. And the ancient Indians actually said, instead of these 4 elements, earth, water, fire and wind, ancient Indians said they were Panchamahabhutas, and they added space. Prithvi, Apa, Teja, Vayu, earth, water, fire and wind, and they added Akash. Akash is space. And this is a statement very similar to Democritus said by Kanada in Vaisheshika Sutras in the Upanishads. But please realize that this is BC or otherwise. This is just philosophy. This is just hypothesis. But next big step really came around 1700 AD, which is what the scientific processes that we all follow were defined, and that was done by by Sir Isaac Newton, and this was the beginning of what Stephen Weinberg called the Age of Enlightenment. So Newton in optics actually defined a process of substantiating the idea, and he said that now the smallest particles of matter may cohere by the strongest attraction and compose bigger particles of weaker virtue. There are therefore agents in nature able to make particles of bodies stick together by very strong attractions, and it is the business of experimental philosophy to find them out. So at the time of Isaac Newton, if you had asked what is the branch of science that deals with what are the elementary constituents of nature, you would have said it's experimental philosophy. So our belief as to what was elementary changed from the 4 to 5 elements of Greeks or the Indian sages, from the BC area to thermodynamics, which describes 3 states of matters, graduating slowly to Mendeleev's idea of chemical elements, which are obtained using systematics of observed properties of various objects. This in later led to Dalton's idea of atoms, which were actually really molecules, and order in atomic weights led to the idea of proton. So in these days, the subject of the science, branch of science, which dealt with the fundamental constituents of nature, would have been chemistry and atomic physics. And the last step that was taken by Rutherford, actually this thing that there are protons and neutrons, as I said, beginning of that step was when Rutherford discovered the nucleus. So the branch of science that explored the fundamental constituents of matter has changed from thermodynamics to chemistry to atomic physics to nuclear physics to now elementary particle physics. And how important is the idea of the atoms? I want to make you realize that something we take for granted, which not very old, long back, in Richard Feynman, who was the very famous physicist in the 20th century, he said, if all the scientific knowledge in the world were to be destroyed, and I can choose only one piece of understanding to be passed on to the future, I would choose to pass on the message that matter is composed of atoms ceaselessly moving and bouncing against each other. So this entire journey that took place from BC to 1800s is actually the journey which helped us understand that matter is made up of atoms. Now, particle physics today has fulfilled Newton's order. And what does the subject deal with? It deals with what are the elementary constituents of matter, what holds them together, but most importantly, what is the mathematical framework which describes how the constituents are put together to form matter, how do they interact with each other, and how can we predict its behavior under different conditions. And this is where the theoretical particle physicists come into play. People like me who would need a lot of mathematics, in fact, to understand the behavior of matter at short distances. At these extremely short distances, classical mechanics of Newton is not enough. You need to have quantum mechanics, actually, you need to use that. And further, you need to have a mathematical framework which will allow you to describe creation and annihilation of particles. So that is really what the subject of particle physics is all about. And trying to understand 2 and 3 together actually taught particle physicists the importance of symmetries, and actually they led to the prediction of new particles, which were then found in scattering experiments, which in turn fueled the theoretical development of the subject. So this is how the subject of elementary particle physics is, and it has developed over the last 125 years. And now today we have, like Mendeleev, we have what we call periodic table of particle physics, and here on the y-axis are the masses of the different particles, and we particle physicists don't give masses in grams because the numbers are macroscopically extremely small. We use instead a set of unit that mass multiplied by c square we all know is energy. A unit of energy can be joules, or a unit of energy can be electron volts, and 1 electron volt is the energy that the electron gains when it falls to a potential difference of 1 volt. In these units, for example, a proton has a mass of 1000, roughly, exactly speaking, 938 million electron volts. So we will measure all the masses in giga electron volts. 1000 million electron volts is 1 giga electron volt. So giga electron volt is my unit of mass. Like I had a unit of distance, atomic distance. So in that unit, in fact, now we know that there exist quarks, up quark, down quark, strange quark, charm quark, bottom quark, top quark. And 2 up quarks and 1 down quark makes a proton. 2 up quarks and 1 down quark makes a proton. 2 down quarks and 1 up quark makes a neutron. Protons and neutrons make a nucleus. Nucleus plus electron makes atoms, and the whole story goes on. What are these additional quarks doing here? Actually, they are produced only in high energy processes, and they are not really contained in normal matter, that is you and me. All the normal matter in the universe is really made up of down quark, up quark, and electrons. But all these additional new particles, which we now know exist, are seen, and we know that they existed at the beginning of the universe, and they are till today also produced in some high energy processes. In addition to that, there are these neutrinos, which, for example, there are neutrinos which are produced in the center of the sun when the sun produces its energy. And then there are brothers and sisters of this electron neutrino, something called muon neutrino, something called tau neutrino. And now you see the one interesting thing. Before I finish the interesting thing, then there exists the force carriers. There are four forces. The strong force which holds the neutrons, protons together in a nucleus, and an up and down quark to form a proton. And then there is electromagnetism, force of electromagnetism, which takes the electron and the hydrogen nucleus and forms a hydrogen atom, and so on and so forth. So the electromagnetic interactions are mediated by photon. The strong interactions are mediated by something called gluons, and the weak interactions, which cause actually the radioactive decay, are mediated by W and the Z bosons. And again, you see the big range of masses, and then of course there is this all-encompassing object called Higgs boson, and this finishes the table of fundamental particles. But what I want to show you and go on is the enormous range of the masses that these fundamental particles have, and these are actually masses that are actually measured in experiments, and that is the achievement of the last 100 years. I should also add gravitational interaction and the spin 2 graviton in this picture. They are not there, but that would complete the entire picture of particle physics and the force carriers, which are either spin 1 or spin 2, and matter particles, which are spin half. So this I will now skip actually, but the fact is that the Higgs was the last particle in this table to be found, and Peter Higgs and Anglais actually got the Nobel Prize for the theoretical discovery of the mechanism which contributes to our understanding as to how the subatomic particles gate these masses, which have been measured, and its existence was actually predicted by Weinberg and Salam in some theoretical formulations. And the machine planning began in 1986. Existence was indirectly confirmed in 1999, and it was discovered in 2012. So this is like, hunting this Higgs was a major expedition and was rewarded by a Nobel Prize. So the question is, was it always so for all the particles? Actually, no. Some were accidentally discovered, some were predicted, but the hunt was necessarily not so difficult and not so expensive. And it is this that I want to try to tell you the journey. So here there is a table. Again, I won't spend too much time because I'm going to start talking about the details of this table. But you can go and take a look at the article in Physics News. And what I want to only you to notice here is that sometimes a particle existence has been postulated on theoretical grounds or on the grounds of observation of symmetries in the properties, and the discovery, has come somewhat later. And in some cases, like the Higgs boson, the postulation was in 1964, some indirect information came in 1999, and the discovery was actually in 2012. For W and Z, the postulation was in 1961. Indirect information came in between in the 20 years, but the discovery took about, up to 1983. In the case of photon, its discovery was its postulation, as it were. So particles have shown different ways. So nucleus was discovered by Rutherford by alpha particle scattering, and that actually began the inward bound journey into the heart of the matter. Pions were predicted by Yukawa, and they were found in cosmic ray experiments in 1947, and these were predicted by Yukawa as the mediators of the force which hold the protons and neutrons together to form a nucleus. Then existence of protons, as I already told you, was inferred from observations, and that of the neutrons from the properties of nuclei, and they were at that time considered elementary. So let's now go back a few, begin at the beginning. In the second of 19th century, Faraday actually postulated that electricity comes in multiples of a basic unit. And what was the experiment that was done by I'm sure all of you know this famous experiment by Thomson, where he took a cathode ray tube, and what he found was that the cathode rays, bent, deflected under the action of electric field, as well as in a magnetic field, and you could actually measure the ratio of the charge to mass of this object, and he suddenly found that these were made up of what he called corpuscles or particles, which had a E by M ratio which was very, very different from the hydrogen ion, and this was the first elementary particle which was discovered in 1897. So I want to take a few minutes to tell you that there were 3 steps in this transition of the electron from being a postulated entry to a physical reality. It took only 4 years. Faraday observed that electricity comes in units from simply patterns in ionization. Experiments made by Thomson showed that the cathode rays behave under the action of electric and magnetic fields as though they consisted of particles with a ratio of charge to mass, the famous E by M, which is very different from the hydrogen ion. And then came the most important step, which we normally do not know, but I want to emphasize it here. A very famous physicist called Lorentz, Dutch physicist, what he did, he calculated splitting of the atomic spectral lines in a magnetic field. You are all physics students, you would have studied that atomic spectral lines are observed using spectrometers. And the prediction of the atomic spectral line splitting was actually agreed with Zeemann's measurement if the value of the E by M that the particle inside the atom had was exactly the same as what was measured by Thomson. So this was the confirmation that what Thomson had seen in his cathode ray tube is actually the same electron that exists inside an atom. So this is from a postulation here by Faraday. This is the physical reality that the electron actually exists. All right. So now then came finally, and this is the Rutherford scattering experiment, which all of you know that there was a beam of alpha particles which was incident on this thin gold foil. So there was a beam, then there was a thin gold foil which was a target, and the alpha particles most of the time actually went undeflected. And how were they detected? They were detected because they hit this zinc sulfide screen and it produced a splash of light, and the splash of light was seen by this microscope, and indeed one was able to then see which paths the alpha particle had taken, and most of the time the alpha particle actually went undeflected. It went straight through the thin gold foil. The foil didn't do anything to it. But some of them actually came back and rebounded. And this was, what the big surprise, it was the big surprise, because Thomson had thought that the atom is like a plum pudding, which means electrons are sitting all over the place like plums in a plum pudding, and therefore the alpha particles, which are electromagnetically charged, should actually get deflected by those electrons or attracted by the electron, because alpha particles are positively charged, and one should see some effect. And that effect was not seen. But on the other hand, sometimes it was really pushed, they were really pushed back. And this is really what Rutherford interpreted, that there is a nucleus of an atom, and he interpreted this that the positive charge of the atom is a point. Now, actually, to quote Rutherford, he said it was about as credible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. So what this observation is telling you, that the most of the atom is actually free space. So the alpha particle go most of the time undeflected, but once in a while they meet something, and that something is very strong, pushes it backwards. So it's like, you are trying to cross a road, and if there is a knot of people at the center of the road, maybe because there's an accident, and if you're trying to cross the road through that knot, you will be pushed back. Of course, people will tell you, go away. But on the other hand, if you go on the side of the knot, there is no problem. So the distance that you have to leave out and the size of the knot, the size of that particular knot, if that is very, very small, larger would be the pushback that you will get. And indeed, that's what this experiment was telling you, that some of the alpha particles rebounded, and they were really telling you that there is a positive charge of the atom which is concentrated at one point, and all the mass is also concentrated here, and the rest of the atom is nothing but space. So alpha particles were able to look inside the atom and see the size of the region of the positive charge, where the positive charge was actually distributed. So the existence of atoms, as I said, beginning from Dalton, was inferred by looking at many properties of matter on macroscopic scale. But the nucleus was actually indicated only in scattering experiments. So if you were alive in 1914, then you would have said everything is made up of molecules, molecules are made up of atoms, atoms contain electrons with a lot of empty space and positively charged point nuclei. That is it. So this was the decade of atomic physics and nuclear physics. So could we have said that the nuclei are the elementary building blocks? No, because already by Becquerel's experiments, people had seen that nuclei actually change into one another. So if they change into one another, radioactivity was found. So you really knew that nuclei were not the ultimate building blocks. But what was also seen, and this was Rutherford who saw this, that the mass of the nuclei came in approximate integral multiples of hydrogen nucleus. So I said, maybe hydrogen nucleus doesn't decay. So maybe hydrogen nucleus is the basic building block. And this began thus the decade of nuclear physics. But then the question came that now I have already told you that the nucleus is made up of neutrons and protons are made up of quarks. So you should ask me immediately, why did Rutherford see the nucleus as a point? But that is very clear. We can understand this very easily by realizing that what is the size of an object, how we measure the size of an object, also depends on the resolving power of the object, of our viewing apparatus. So when we use microscopes, and you notice that when you want higher resolution, you use smaller wavelengths, and higher the energy, therefore higher the resolution. Now, here we are using alpha particles to look inside, and it is the wavelength of the alpha particle that decides what is the smallest distance where you can resolve the 2 points as being 2 separate points, and that will be 1 wavelength of your beam. And if you calculate the wavelength of alpha particles, which have an energy of million electron volts, by using de Broglie's relationship, you can actually show that they correspond to a wavelength of 10 to the minus 2 angstroms, and the nucleus actually has a size smaller than 100th of an angstrom, and therefore Rutherford thought that the nucleus was a point. So now, to understand whether the nucleus was made up of something smaller, one needed higher energy beams. And in fact, Rutherford has gone on record by saying that it has been long my ambition to have available a copious supply of atoms and electrons which will have energies transcending those of the alpha beta particles. Protons and electrons actually therefore were accelerated to high energies after this demand of Rutherford, who was of course the greatest scientific leader of that era, and people in the laboratories working around him actually built accelerators, and they were Cockcroft, Walton and Van de Graaff, all British actually. And that this development since then in high energy physics actually has gone hand in hand with the development in accelerating particles to higher and higher energy. So this is where we very often call the subject of particle physics as the subject of high energy physics. So this was a Cockcroft-Walton accelerator which fitted inside a room. This is from 1931, and this was simply sending the electron to huge potential difference, and then you needed to shield everything so that they won't spark, and this fitted inside a room, and this accelerated objects to about 1 million electron volts, but this was about the limit that they could do. Whereas on the other side of the channel, sea, Atlantic, in fact, Lawrence and Livingston discovered in the US the first cyclotron, where they could accelerate the particles using magnetic and electric fields simultaneously in a very small size. And this was the first accelerator, which is the size of a quarter actually, as you can see, 4.5 inches. And then later on they built a bigger model which was 11 inches, still not very big, 1 foot, which will be this much, and they could accelerate to about 1 million electron volts. So now one could do a lot of experiments using these accelerators, and people started seeing many different things. They studied patterns in nuclear masses, they studied the spin angular momentum of the nuclei, And they realized, yes, indeed, nuclei are made up of smaller units, and they were protons and neutrons. And at that time, the size of those objects, neutrons and protons, was smaller than the least count of our vernier calipers, as it were, and therefore we thought that maybe they are elementary. So the fundamental objects at that point were the photon, the electron, the proton, the neutron, and one more very important object called the neutrino, which was actually postulated by Pauli by looking at beta decays. Beta decays were discovered by Becquerel really long time back. And people had studied in the days of nuclear physics, by studying the nuclear beta decays, one understood a lot about nuclei. And these beta decays, where a nucleus with Z protons and N neutrons changed into another nucleus with one less proton and one more neutron, or one more proton and one less neutron. So it effectively converts a proton into a neutron, or vice versa. Associated with this, an electron or a positron is emitted. And a free neutron was indeed discovered by Chadwick in 1936, and therefore it found that the free neutron actually decays into a proton and an electron. But the energy of the electron seemed to vary continuously in beta decays, also in the neutron decay. Now, if that's happening, that's a big puzzle, because there is an energy that is released in the reaction. That energy is shared by these two particles. And how can one of the object can have completely different energy? Because proton was found to be more or less at rest, or here the nucleus was found to be more or less at rest, and the energy that was released was not all carried by the electron, but only some fraction of the energy was carried by the electron. So people said, oh my God, does it mean energy is not conserved? Also, angular momentum is not conserved. But that is where Mr. Pauli came and postulated neutrino to preserve the conservation of energy, conservation of angular momentum, etc. And then he said this small neutron, which is called neutrino, is a neutral particle with spin half that gets emitted in beta decays. And here I want to take a step back and tell you that this is an example of a symmetry predicting existence of a particle. Now, this was told to us by Amy Noether. This is because of a theorem that Amy Noether proved, a famous mathematician, but she proved a theorem which was of great use to physicists. And she proved this theorem that all conservation laws are related to some symmetry or the other. And she said conservation of energy or the conservation of linear momentum actually depends, is guaranteed by the simple fact that the laws of physics do not depend on the position where you perform the experiment or the time in the, whether you perform the experiment today or yesterday, whether you performed it yesterday or whether you will perform it tomorrow. The law of gravitation that you will find at the pendulum, during your pendulum experiment, the gravitational acceleration constant will remain the same. And this simple homogeneity of space and time actually tells you that energy is conserved. So this is an example of an invariance which is being used to posit the existence of the particle, and this happened again and again in particle physics. So anyway, at this point, if you were, a particle physicist, nuclear physicist living in that time, you would have said that now, yes, nucleus is not an elementary object. It's a composite of neutrons and protons. And now the list of the elementary particles, as I said here, would then be indeed neutrons, protons, photon, electron, and a neutrino. Now one goes on further and says that are neutrons then elementary? Now this is where people actually already knew that the neutrons and protons cannot be elementary. And why did they do that? They did that for various reasons, and I'm not going to go on with the story. But here I want to show you and discuss to you in a few minutes. I am sort of going to wind down in another 10-15 minutes. So protons and neutrons, have very similar masses. Nuclei is made up of them, and both have spin half. And proton-proton, proton-neutron, and neutron-neutron forces in nuclei are very similar in strength and range. So this was actually inferred from the properties of what are called mirror nuclei. So Heisenberg and Fermi, in different ways, made a hypothesis that one can imagine the proton and neutron as two states of a particle, which we will call a nucleon. So nucleon with an internal spin, I spin in the up direction, is a proton, and a nucleon with an internal spin in the down direction is a neutron. This was in analogy by thinking that an electron which spin up is indeed an electron which spin up in the one arbitrary direction, and then the electron which spin down. These are the two states in which an electron can exist inside an atom, and we had studied that in atomic physics. So this was an extension of that idea. So in a rotation in real space actually changes the state of an electron which spin along the positive z-axis to a state with the spin along the negative z-axis. But if I have only electrostatic potential, we are not able to detect the difference between these two states of an electron. So electron which spin up and electron which spin down. And the fact that the electrostatic potential cannot distinguish between two electron states is because the electrostatic potential depends only on 1 by r, does not depend on the direction. It's invariant under a rotation of coordinate axis, and that is the relationship between the fact that as long as I'm looking at electrostatic potential, electron which spin up and electron which spin down are kind of two states of the same particle. So similarly here, people postulated that a rotation in the hypothetical internal space will convert a nucleon with spin up direction to a nucleon in spin down direction, that is the neutron. And since we find that the interaction between two protons or two neutrons or a proton and a neutron is exactly the same, this observation is now used to postulate that the interaction between two nucleons is completely invariant under a rotation in this internal spin space, just like the electrostatic potential between the two electrons is completely invariant under a rotation of real coordinate rotations. Now this was the idea of internal symmetry that was first introduced, and this actually gave a lot of order to a lot of properties of neutrons and protons, and people were beginning to think that maybe this is our glimpse of a final theory. But at that time, there was a zoo of particles that was found in cosmic rays and in accelerator experiments. They are all just like protons and neutrons. So now people started worrying that all of these cannot be fundamental. And then Gell-Mann and Schweitzer independently presented an extension of this I-spin idea that I have told you, which was introduced by Heisenberg and Fermi, extended by Fermi. And they extended it further, and then they said that all the observed particles, protons, neutrons, lambdas, these were the zoo of particles, or antiprotons were also found. They are made up of some fundamental other spin half objects. 2 up quarks and down quark make a proton, 2 anti-up quarks and 1 anti-down quark makes an antiproton, so on and so forth. A pion is made up of an up quark and a down anti-down quark, etc. So this is how the UDS quarks were first arrived at, but they were postulated. Now this observation by Gell-Mann and Schweitzer actually said that all the regularity that was observed in the properties of the members of this particle zoo could be explained by saying that they were made up of constituents called quarks. But nobody could break up the protons and neutrons into quarks. So most of the physicists said that, my God, quarks are not real entities. But there's some kind of mathematical abstraction. Let's go on with this. In fact, there were chemists till Einstein showed Brownian motion. They always believed that atoms themselves were a mathematical entity, and that was useful to explain the gas laws. So that, this is being repeated at the level of particle physicists. But actually, I will not blame the particle physicists too much, because these quarks were required to possess fractional electrical charges. That is 1/3 or 2/3 of the charge of an electron. So at the time, people really said that these quarks are not real. They are just an abstraction, which helps us understand this entire property of fundamental particles like protons, neutrons, lambdas, antiprotons, so pions and kaons. So let's go on with this idea, but let's not believe that they really exist. At the same time, Gell-Mann actually predicted the existence of a particular particle called omega with its mass, and experimentalists found it at that mass. So therefore, he got even the Nobel Prize for the idea of the quarks. But at this point, people really began to think, my God, where are the quarks? Can you do a Rutherford type of experiment and see them really? Can we break open a proton? How can we break it open? And this is the basically people decided to do an experiment which is an analog of Rutherford experiment. Here they took a beam of electrons instead of the alpha particle beams. It was incident on a nucleus or a neutron and a proton, and what was found, what was detected was the electron coming out. Remember, in the Rutherford experiment, there was alpha particle beam, there was a thin gold foil, and the detector was the combination of the zinc sulfide screen and a telescope which was counting the scintillations. Now the situation was a bit more complicated. I will show you the real detector in a few minutes, but the arrangement is always the same. A beam hits the target and a scattered beam of particles are detected by the detector. I told you that the wavelength of the beam of particles would actually then be capable, will decide what is the scale at which we can probe the existence of a structure, and the wavelength of the electrons, which had energy of about 400 to 600 million electron volts. That means that the mass, the relativistic mass times the energy of the electron was about 600 million electron volts. And if you calculate the wavelength, it's about 10,000 times smaller than the wavelength of the alpha particles. Now count the number of electrons that are scattered at an angle theta and compare it with what you expect if the nucleus was a point nucleus or a point-like proton. So this was the famous experiment. This was the Stanford Linear Accelerator, which is a mile long in fact, and which accelerates the electrons by passing the electrons through a series of potential differences till it reaches this lab here, and inside the lab there was this detector. And look, this is the size of the detector, this is a person, so you realize that the sizes of the detectors and the beams and the energies, everything has gone up much more than the Rutherford experiment. And here the scattered electron is detected in this detector, and this detector can be moved along at few angles. This was a very heavy detector, and this was an experiment that was performed by Hofstadter. He actually got the Nobel Prize for that. And what his experiments proved that the nucleus and the protons did have a finite size, just like Rutherford's experiment told us that the atom was made up of a lot of empty space and a point nucleus. Now we are beginning to see that the nucleus is a lot of empty space and a few nucleons, and a proton is a lot of empty space and a few quarks. That's what really this experiments did. So first let's look at the nucleus. We found that the nuclei were about 10,000 to 100,000 times smaller than the atoms. That is where that number that I gave you on the first slide came from. And we were actually, I think nuclear physicists were quite happy, because they already knew that the nucleus was not point-like. Nucleus considered of nucleus was known. So therefore this was actually what you call in chemistry a confirmatory test. But what happens to the proton? So Hofstadter actually did the experiment where he replaced this nucleus now by a proton, and he increased the energy of these electrons by about a factor of 10 or 20 in fact. So he increased the energy by a factor of 20. That means the wavelength was reduced by a factor of 20, and that indeed told them that even the proton has a finite size, and this size is 100,000 times smaller than an atom, and that's 1 Fermi. How did it happen? Because you studied the scattering of an electron and a proton, and what you did, you measured the electrons with which were scattered at an angle theta. The angle theta was fixed because mind you, the detector was very heavy, so you took readings at a fixed angle theta. When you took readings at the fixed angle theta, using particle kinematics, you could calculate the energy of the scattered electron must have, and indeed you measured all the electrons that came out actually did come out with the same energy that you expected for a given angle theta, and this detector could be moved through 3 angles, and the energy of the electron could be changed. And as a result of that, by doing the experiments, one was able to confirm that the proton actually has a size. But the real surprise came when the electron energy was increased further. So now we had here 400 to remember, here we had 400 to 600 million electron volts. You increase by a factor of 20. That means you went to 1 GeV to 5 GeV. And now this 1 GeV to 5 GeV was increased even further to 20 GeV. So now the resolution of my beam is about 100th compared to the size of the proton and neutron. And then something very strange happened. You were expecting at a given angle theta electrons of a given energy EE prime. You could calculate given the value of the EE and the value of theta. But now if you calculated the EE prime, you found that the actual scattered electrons did not have that energy, but they had energy over a whole wide range. Now this indeed then said that the scattering was not taking place just from a proton, but the scattering was taking place from something inside the proton. And indeed, when you increase the energy of the electron further, the scattered electron again started having a unique value of energy, but that energy value was different than the energy value that was computed for the proton. And indeed, it was actually 1/3 the value of the energy that was computed for a proton. So people then realized that, aha, the proton consists of 3 objects, and these 3 objects, they are point-like as far as this incoming energy of the electron is concerned. So this is how the elementary quarks inside the proton were actually revealed, just like Rutherford's large angle scattering revealed existence of a point-like nucleus inside the atom. Exactly the same thing. And this is what Gell-Mann's model needed. So now we are coming to the end of the road. The quarks made actually a second coming. Measuring the electron energies for different angles, the spin of scatterers could also be determined. And they seem to have all the properties that the quark model required, even the funny 1/3 and 2/3 charges. So here, the scattering experiments substantiated the conclusions that were drawn by Gell-Mann and Zweig by observing the patterns or the symmetries. But actually, these scattering experiments did something more. The same experiments also showed that there existed scatterers inside the proton which cannot see the electron because they are electromagnetically neutral. But the scattering experiments were able to indicate their existence from energy momentum conservation. And in fact, the theory of strong interaction, which was being developed around the same time, such neutral force carriers were actually required. They were called gluons, and the theories were saying that the proton should also have gluons inside it. And lo and behold, the scattering experiments were able to probe the number of such gluons, the structure of what energy fraction of the proton energy is carried by the gluons, and we got the first glimpse of the gluons and the first clue to the correct theory of strong interactions in the same scattering experiments. And this actually got the Nobel Prize for Physics in 2004, but the theory was put forward in 1974. I'm trying to show you how slowly the time difference between when the theory postulate was made and when it was experimentally established, the gap actually increased substantially slowly. In the electron case, it was 3 years. In the case of the quarks, it was again something like 10 years. And in the case of quarks and gluons, it took 30 odd years for the experiments to confirm that the quantum chromodynamics was the right theory. Now, if you keep on increasing the energy of the electron further, very naturally, you can ask me what happens. Now, what we find as the number of constituents inside the proton goes on increasing, but more and more quarks and gluons are actually created inside the proton. But it's not as though, they get created through the energy that you are pumping into the system, and energy just converts itself into quarks and gluons, but there is nothing else inside the quark. That is the point. So the increasing energy tells us that there are no new constituents now. We only see increasing number of quarks and gluons, and this increase in the number of quarks and gluons is something that we can compute from the theory. In fact, I have worked on this part of the theory of strong interactions in my youth, and indeed what you find experimentally completely agreed with the predictions of the theory, and therefore now we know that at the highest energy of the electron at the current level of experiments is 100 billion electron volts, and we have found no evidence for any substructure of a quark up to 1,000th of a Fermi, that is the 10 to the minus 18 meters. So now I have come to the end of my inward journey. So is this the end of road in substructure? Actually, yes, we think so. Are we saying this simply because we don't have enough high energy probes? Answer is no. And there are two reasons for this answer. One is that the dynamics that I kept on talking, that I did not talk about, but the theoretical understanding of interactions actually comes here into play with full strength. And scattering is one way in which we hunt for what is at the heart of the matter. The other thing is developing this theory. And at present, every single piece of experimental observation agrees to a very high degrees of accuracy, sometimes better than 1 part in 100 millions, with the predictions of the theory, which treats these quarks and leptons as point-like up to energies of 10 billion electron volts. So this is like a thought experiment, and you know from this thought experiment that we have an indirect but very, very strong proof that the quarks and leptons are point-like and have no further substructure. But the other, this has continued now, and this is what the Large Hadron Collider experiments do. There is a proton and antiproton beam, they hit against each other, and now you probe the dynamics of the fundamental constituents and interactions by colliding these beams. And when you collide these beams, it's actually the quarks and the gluons inside this which collide with each other and then produce various new particles. You study how they decay, and that's part of what the LHC is doing. But many, many paths need to be traversed simultaneously to arrive at the truth of nature. I followed only one path and one track of the journey that the particle physicists followed. And this was the question of what are the ultimate constituents of matter. The second track, which I mentioned briefly, is how to find the mathematical framework which describes these elementary interactions. I have presented the journey into the heart of the matter by probing it with higher and higher energy probes. Whereas all this would have been impossible without corresponding strides in our understanding of the dynamics. And Large Hadron Collider has finally found the evidence for the Higgs boson. And just like atoms, electrons, and quarks were realities, earlier experiments had shown us, LHC showed us that Higgs is also not a figment of our imagination. So is this the end of the road? Is the journey over? And that is where this connection to the edge of the universe comes into play. Is it just because we want to keep ourselves in the business? No. Because there are many cosmological observations which still lack an understanding. And these puzzles are of relevance for particle physics because theories of particle physics have cosmic implications. In fact, this whole story of what is called astroparticle physics is to me the future of particle physics. And this was started by giants like Bethe, Gamow, and Weinberg. They pioneered these cosmic connections of nuclear and particle physics. So this is a very nice picture I have taken from the web page of Particle Data Group. And this shows us the history of the universe. As Gamow said, it took us less than an hour to make the atoms. It took the nature or the universe millions of years to form the stars. And it has taken billions of years to form the man. And it is this history of the universe. And this history of the universe, initially it started with the Big Bang. It was pure energy. And here, Large Hadron Collider actually can probe this period in the history of the universe, which is very, very few, 10 to the minus 10 seconds after the Big Bang. And later on, with experiments like Planck, which measure the cosmic microwave background radiation, then they probe the physics of what happened in the history of the universe in about after 1,000 years after the universe was born. And in all this entire journey of the universe, from here to here, in the early stages, laws of particle physics play a very, very important role. And indeed, in an expanding universe, the early times mean distances which are very far from us right now. And that's why I said that the particle physics is of relevance for the measurements we do at the edge of the universe. These are the things that happened billions of years ago and things that are happening at the edge of our universe. I had planned to show you a video, but I will put the link in a chat box and please see the video yourself to give you an idea about the distance scales that are being projected, or the time scales that are being projected in this picture. I will leave that out right now, and I will come to almost to the end of my story. So what happens is that right now we need to go beyond the standard model of particle physics, and there are three very big cosmic reasons which I mentioned already, namely that there is dark matter in the universe. There is matter in the universe that we cannot see. There is matter and antimatter asymmetry in the universe, and the universe seems to be expanding and accelerating. Particle physicists have a few more reasons, because theoretically we cannot explain why the Higgs boson has the mass it has. We cannot explain why neutrinos have non-zero masses. We cannot explain why the masses of the different quarks and leptons vary so much over many, many orders of magnitude. And therefore, particle physicists actually are probing these ideas. But the interesting thing is that all these ideas actually have implications for all these puzzles. And these puzzles are being studied in the physics of the cosmos and physics of the universe. So right now, terrestrial experiments and those in the sky have to probe the wonders of nature in fact together. We will probe the universe to very many different probes. The optical, India has Hanley, a big optical telescope in Hanley laboratory. The radio telescopes, which are GMRT in near Pune, and a square kilometer array of which I showed you a picture. The Laser Interferometry Gravitational Observatory LIGO, neutrinos, there is IceCube, there is Dune, and then there is Indian Neutrino Observatory INO, and colliders, which are Large Hadron Colliders, and perhaps International Linear Collider. So these are all multi-wavelength probes of the particle physics at the heart of the matter and at the edges of the universe. And I will end my talk with showing you a picture of sun which is taken through the photons. That is the real picture, that is what we are used to. And this is a picture of the sun as taken by a neutrino detector in Japan. And you can see actually that the two pictures are pretty, they pretty very much match. And on the earth, we can photograph a sun through photons. We can photograph the sun through the neutrinos. And now we want to do much more with this simultaneous multi-wavelength probes and try to understand what is the equation that describes the entire universe. That's where we are all going, and that's where this is the story. The future of particle physics is the physics at the heart of the matter along with the physics at the edges of the universe. Thank you very much.
Thank you, Rohini. Well, I was engrossed, and I didn't even realize when you kind of came to the last portion and said you would stop now. I looked at the watch surprisingly, that why are you stopping so soon?
It was a bit long. I'm sorry.
No. I mean, in fact, I'm saying the other way, that I was surprised. Okay. There are questions on YouTube. Will you take some questions?
Sure.
Yeah, Shiv Kumar.
Yes. Two questions, similar questions. I'm merging them together. Question one, ma'am, can we really see quarks or just get an image that corresponds to it? Because as per me, the visible wavelength of light is not so less. This is one question. And another question is...
Second part, I understood. Let me repeat. The first is, can we really see a quark?
Or
can we take a picture? That is the question.
Yes.
But the second half of it was what?
No, second half is that student is saying, because as per me, the visible wavelength of light is less.
Very good. No, that's a very good question. I understand the question. I will answer.
Right. Another related question is, what do we mean by seeing a tiny particle through an electron microscope?
Okay. Now, I think these are fair enough questions. And the point is, indeed, we don't see it. When I say that we see our DNA through an electron microscope, what we see are diffraction patterns. And we convert those information obtained from in the diffraction patterns through our formulae to figure, it's like, I think some of the students at least would be familiar with what is called the X-ray crystallography, at least in the BSc. That is, you want to determine how different scattering centers are situated in a crystal. What you do is that you look at the diffraction pattern. And then from there you try to figure out what is the distance between the two scattering centers. So this is very similar to that. This is an information that you're going to extract out of the numbers, out of the intensity of the electrons that are scattered at different angles, and you're going to do a calculation. So it's not as though that you're going to visually see anything. In fact, sometimes when I give a talk, I give the photograph, what is called a field. It's a good question, so I will give a small story that the fact that the question that you are asking, I don't know the student, but this was a question that a lot of people wanted to know, how far can we go and see things visually? And the most we can do visually is what is called a field ion microscope. And that was actually, I'm proud to say that one Indian, Bahadur Singh, was actually involved in designing this field ion microscope. And there you can actually see an image of the tip of a tungsten needle where you can see the atoms. But that's about as much as you can do if you want to visually get a photograph. That's the last. Beyond that, nothing is seen even as a picture. Indeed, you are right that the wavelength of the light is much, much bigger than these distances that we are talking about. But that is why we cannot use light to see this. We have to use the analog of light, and that's the electron beams or proton beams, and which is basically why we have to thank Heisenberg, de Broglie and Einstein, because they made us realize that we can go beyond the limitations of the light and picture things beyond it. So when you see things in radio, for example, radio telescopes, then also you don't see any pictures. Radio telescopes also only measure wave diffraction patterns. So frankly, every seeing is diffraction patterns. Now, that is the simplest answer, and I think this is something you can take up. I can tell the student, you can take up and look at any simple book which talks about X-ray crystallography or something like that, and which will explain this in some detail. Okay? I hope he or she, I do not want to assume it's a he, so either a he or a she, I hope the student is satisfied.
Okay. So another question is gravity a wave?
Gravitation is definitely a wave. See, as right now what we have understood, it's like asking, is photon a wave? See, Newton told us photons were corpuscles. Then Huygens came and said photons are waves. Then Einstein came and said photons are both. Photons are particles and photons are waves. And then Maxwell and Faraday explained to us that electromagnetic light propagates as electromagnetic waves. Then we saw radio waves were also electromagnetic waves. The same way, gravitational field corresponds to gravitational waves. So gravitation waves exist, and that's what we detect. We actually detect real gravitational waves, and we detect interference patterns that are produced by gravitational waves coming from two different, at two different sources, in fact, two different places. And the reaction of two different targets to the same gravitational wave disturbance.
Maybe the student is asking, electromagnetic waves follow Maxwell's laws, right?
Yes.
And so what is the corresponding law here?
Oh, okay, that is a bit more, okay, thanks for interpreting the question, because I was not able to see this aspect of the question. All I can say is that just like Maxwell's equations, and we know the law of propagation of the electromagnetic waves, we can also derive laws of propagation of gravitational waves. Except that the gravitational waves are slightly more complex, because in the electromagnetic wave there are 2 degrees of polarization, and that's where you finish. You know that there is an electric field, there is a magnetic field, there is a direction of propagation, and the 3 directions are orthogonal to each other, and the description is very simple. In case of gravitational waves, it's a slightly more complex picture, because these are spin 2 particles. So it's a tensor wave. So there are there is a transverse polarization, and then there is a longitudinal polarization. So there are these, like the light, there is this plus and minus 2 degrees of polarization. But then there is a shear, which doesn't exist in the case of electromagnetic waves. So the shear of space-time itself is the another degree of freedom. And that is why gravitational waves are a bit more complex to describe in complete analogy with, they cannot be described in complete analogy with electromagnetic waves. But they are waves which carry basically shear with them. Electromagnetic waves do not carry any shear.
In flat space.
Yeah.
They're in flat
That
space.
is how I can,
Okay.
at least right now, this is the best I can do to explain this question, in fact.
Okay. Another question is, we know the Earth's revolution time around Sun is 365 days. How long do electrons take to make one revolution around the nucleus typically?
Around the?
Is it the same? Nucleus.
Okay. Actually, that is something, I don't know what the student is, but if he or she is a BSc student, then when you study the Bohr atom model, you can actually calculate the velocity of the electron in the first Bohr orbit, and the velocity of the electron in the first Bohr orbit is actually 1/137 the velocity of light. And now if you know the radius of the orbit in the simple picture, in the semi-classical picture, you can calculate the time it takes. The velocity of light is 1/137 the velocity of electron in the first Bohr orbit is 1/137 the velocity of light. And the radius of the first Bohr orbit, everybody knows how many angstrom it is. Please calculate now the time by dividing the distance by velocity, or vice versa. But this is a calculation that can be done trivially.
Okay.
2 pi r is the distance, r is the radius of the Bohr orbit, which is a few angstroms, and he or she can do the calculation.
Okay. My internet is a bit shaky, so I'll turn off my video.
Let me increase the volume because
how
I'm not
much
able
of
to hear you, Shivkumar. One moment. Tell me.
Oh, okay. How much of electric energy does a particle collider typically use up in a day? Is it comparable to that of a city in a day?
No, that's an excellent question. I may not be able to tell you megawatts correct to the last megawatt, but I can tell you this, that in the months of winter, the laboratory near CERN, in fact, shuts down its operation because the energy requirements are close to the energy, make a big fraction of the energy requirement of city like Geneva. So this should give you some idea that the energy requirements are indeed very high. So one of the things that the new accelerator developments are doing is trying to devise what they call green accelerators, where you can use less energy, because you're completely right that in a particle collider I have to pump the energy, quite a lot of it, and therefore traditionally the accelerator in Geneva shuts its doors, puts the shutters down in December 18th and opens them again on January 15th or January 18th, because in the winter months it's completely becomes super difficult to maintain the energy balance. So it's a substantial fraction of the city's energy budget. Yes. And just to tell you that, since I don't know how much this person knows, but the major energy that is required in an accelerator is to put it in the cavities, because you take your electrons or protons and you make them traverse inside a radio cavity, and every time they pass the peak of the laser field, the laser field kicks the electron and gives it energy. So the major chunk of energy is in powering these radio frequency cavities, and that's where the accelerators need a lot of energy, nowhere else. That is the real kicker, as it were. The rest of the energy is not very high.
You mentioned that India. Sorry, Shiv. A related question. She just answered about the energy use. So there's a related question. The Indian version that is coming up, is it a green energy?
India doesn't have a collider. What we are doing is a neutrino observatory. So it's a passive thing, in fact. What we do there is we stack together a whole lot of iron plates, what are called resistive plate chambers, and they are stacked within layers of iron. So we are going to create a giant magnet and we are going to power that. Now that also will require some energy, but not huge, because that is just the current that is required to make a big magnet, which would not be very much bigger than one of the big power plants or any one of the other big installations. So what the Indian facility that we are trying to develop is not an energy consuming object. It is the colliders which are the energy consuming object. In INO, we are actually sitting passively waiting for the neutrinos which are accelerated outside and which are coming and hitting us. So in that, hitting the detector, that is not us, because we don't provide so much mass for them to hit us. So I hope I answered your question. Or did I misunderstand your question?
No, that was it. Okay. How is the Indian thing different from the other?
Yeah, because there are two different kinds of things. One is a collider, and one is these are neutrino experiments, are passive experiments. So they just have to make very huge detectors. So we are making a detector out of iron. The detector in Japan is made out of a whole lot of water. They just fill heavy water and they look at the scintillation in this heavy water target. So there again, the energy is required is only not huge, because the energy required is to maintain the pressures, maintain the vacuum, but those are not much bigger than the normal big industrial installations. The colliders are the real energy guzzlers, frankly. They are like the impalas of the old days. They guzzle the energy, yes.
Ma'am, do we have time for another question?
It's up to Tirthankar.
Yeah, it's still fine. Yeah.
I'm happy to answer.
Okay. So the question goes like this. The Higgs field gives mass to elementary particles, and gravity works with bodies having mass. So can we say gravity is there because of Higgs field?
No. Because this fact that the Higgs field gives particles mass is kind of a populistic way of explaining what the Higgs field does. But in reality, what the Higgs mechanism does is it explains to us why the laws, weak interactions are very funny. Weak interactions are felt only by particles which we call left-handed particles. That is, particles whose spin is opposite to their direction of motion. And what we find is that weak interactions like beta decays, only the electrons which have spin opposite to their direction of motion feel weak interactions. Now that is nothing terribly wrong in it, except for the fact that if the electron has a mass, then by simply changing the Lorentz frame or my frame of motion, I can say that the electron, let's say I start in a frame where the electron has a spin opposite to the direction of motion. Then I say I go to another frame which is moving in the same direction as my particle and exactly at the same speed. Then my electron will come to rest in that frame. And if I take a frame which travels with a bigger velocity still, the electron will change its direction of motion in that frame. So in one frame, the electron will have spin anti-parallel to its direction of motion. In another Lorentz frame, the electron will have spin parallel to its direction of motion. And if weak interactions are felt only by the particle where the spin and momentum are anti-parallel, then you wonder now what the heck is happening. Are weak interactions not the same as you change your frame of reference? And Einstein taught us that velocity of light, for example, is the same as you change the frame of reference. So laws of physics should not depend on my frame of reference. And this puzzle you can explain if there exists interactions of electrons with an additional field called the Higgs field. Now this is really what it is, except where the particle doesn't have a mass, then you can actually be happy with the electron spin and momentum always being anti-parallel to each other, because you can never go to a frame where the electron comes to rest. So the fact that you get this problem is only because electron has a finite mass. If the electron had zero mass, I could never go to a frame of reference where electron comes at rest. So I could never transform a state with spin anti-parallel to its direction of motion to another state by simply Lorentz transformations to a state where the spin and momentum are parallel. So this puzzle or this paradox exists for electrons with mass, and I can explain this paradox by simply postulating the Higgs field. This is what Higgs did, Higgs and Anglais. And I would like therefore to say it very clearly that Higgs particle does not give a mass. And that is a populistic way of saying it. Higgs particle explains why particles can have non-zero mass, and at the same time weak interactions only are felt by particles where spin and momentum are opposite to each other. So it's a highly technical statement, in fact. So let's not oversimplify. I mean, it's not that Higgs. I know that I am also guilty. Many people say this, but I actually like to always say, and I try to be careful. I say that the Higgs particle explains why you can have particles with a non-zero mass interacting with having weak interactions which are felt only by one set of particles and not by other set of particles, which are related to each other through a Lorentz transformation. So that's a paradox which Higgs fields helps us to solve. It's a very important theoretical achievement. But please let us not think that Higgs field gives masses and therefore there is a relationship between Higgs and gravity. No. And actually maybe I should add one thing more, that the mass of the proton, for example, very little of the mass of the proton comes from what the quote-unquote Higgs field gives it. Most of the mass of the proton comes because the gluons interact with each other. So most of the mass in the universe actually comes from the interactions of the gluons with each other, which have nothing to do with the Higgs field. So maybe that's another reason why you should delink Higgs and mass and gravity from each other. Okay? No, it's a good question. So I compliment them for the questions, but I hope that they get something from the answer.
Right. One more question is about the acceleration of universe. So how do we measure the rate at which universe is accelerating, and what is causing the acceleration? Will it ever stop or will it go on indefinitely?
Now, these are very difficult questions, and I am out of my I'm not as conversant with these things because I'm not an astrophysicist or a cosmologist. So I won't be, I have a general understanding, but I won't be able to tell you very specifically, but I can tell you how acceleration is measured. That is something that I can try to explain. And this has to do with observing what are called standard candles, that is supernovae. And so in that case, what happens is that if you want to measure acceleration, you first need to measure the distance at which some object is with us, and then measure the rate at which the distance is changing. Now, in cosmos and the universe, how to measure the distances themselves is a big story. And then now the question is, how do you measure the distance? And then how do you measure the rate of change of that distance? So, because only thing you measure is the light coming. Only thing you have are spectrographs. You have nothing else. And from those spectrographs, you have to actually figure out at what rate the object is moving, at what distance the object is set. So that is where the supernovae are very, very useful, because you actually know precisely the luminosity of these objects when they become supernovae. So then once you know the luminosity, you know the amount of light that is emitted in a steradian of angle at you, and you know when it became supernova. As a result of that, you are able to make very accurate measurements. Given that, that gives you a calibration. And then the rest is simple. You actually measure the spectrographs and you try to see how the spectral lines are changing with respect to distance. Change of the spectral lines is going to give you the velocity, the Doppler shifts, and that's where you are going to measure the acceleration. So measurement part is somewhat simple. What is causing the acceleration, I think none of us know. That is why we call it dark energy, and that's a very, very active area of research. And many theories of gravity or extension of gravitational theories are indeed being postulated to understand the dark energy. So it's an extremely active and interesting area of research. If I knew the answer to that question, I would straight go to Stockholm. It's that important. Okay? But it's something that we don't understand. Let us be honest. We don't understand, but the clues we have are from the early universe measurements. The clues we have are from the energy depositions in the early universe, which we try to understand by looking at the measurements of the black body radiation that the Planck measures, microwave background radiation. So it's like, it's detective work. It's like you go and look in the forest for footprints of a tiger, and then you say, oh, I have seen a tiger. So now all we can see is the footprints of that early universe history on the microwave background radiation. And all the things that we are now trying to understand comes from our good measurements of the microwave background radiation. That's the real measurement that we can make, and the earliest in the universe, in the history of the universe. So I guess, this is as qualitative but as complete answer I can give.
I think we shall close now. So thank you, Rohini, for the very nice talk and for long discussions on things that we did not know. And maybe if Kumar or Shravan, you want to say something for tomorrow's program before we close?
Yeah. So I'll just share my screen.
In the meantime, Professor Godbole, we do this thing to incite the curiosity of the students, and now that they have been incited, is there some way, some place that they can look to for their for answers to their questions? Can they email you perhaps, or do you have?
They can email me. I will give them resources.
Okay, that's
you can
great.
share my email ID in the institutional email ID, rohini@iisc.ac.in.
Yes.
Please share it. I will give them resources.
That's very good. Thanks.
Because most of the material is available quite easily, and I will direct them. No problem.
Thanks very much.
And I see a question in the chat box that how is it that the changing just the number of constituents in an atom changes the properties so much. So I want to tell, it is the game that the electrons play. As a matter of fact, Rutherford has a very famous statement which said that chemistry is nothing but the physics of the last electron. So it is the games that the electrons play that change the properties of all the atoms so much. So it's not so much changing the number of constituents of the nucleus, but to keep it neutral, you have to change the electrons also. And it is the electrons that decide basically what's happening. I mean, how you transmit light, how you reflect, how do you react to the heat, how a metal or a material reacts to light. It all depends on what the electrons do. So that's really it. It's the physics of the electrons.
Okay. Thank you, ma'am. Yeah. This.
That's why Mendeleev was able to see the tables so well, no? Because he saw that the properties of the elements with the same number of electrons in the free orbit were very similar. They were all, some of them were volatile, some of them were colored, deep colored, some of them were, simple colors, something like that. Okay?
Yeah.
All right.
Okay. So I'll just share a bit about
sorry,
this.
Shravan, I'm sorry you were doing this and I stopped.
No, that's okay. That was indeed my question. So, so this was the 6th talk in the series of this Science Week, and tomorrow will be the final talk that will be on the topic of magic of math through paper folding. So this will be again, although it's a student special, I think it will be appropriate to any age group, even for adults or college students or teachers. Yeah. So I think all of them will have a great time with this. This will be tomorrow. The timings is 4:30 to 6. And we also have a question fest. This is both for students and teachers. The main aim is to inculcate this quality of asking questions by observing, right? So today there were a lot of questions which were again expression of your curiosity, right? So we want to inculcate this quality in both students and teachers. So we have a very unique contest. Generally, you would not have seen contests like this. So more details will be shared in due course of time. There is also a course, especially for science and maths teachers. This is based on the vision of NEP, right? So to bring elements of active learning into the classrooms. So this will be a 12-session course, and this is a certificate course. And more details on the schedule and how to register will be shared via email. So we'll see you tomorrow.